This is the first video in a series that I'm making to support a course that I'm teaching in ring theory, and we're going to call that course Rings and Fields. And an interesting thing about this course is it will not assume any knowledge of group theory. In fact, I doubt we'll ever even define the notion of a group, although we might kind of offhand, but we definitely won't work with groups. Another thing I should point out is that it will assume knowledge that you might have learned in like an introduction to proofs class. So that will include things like congruence mod n and the Euclidean algorithm and stuff like that. Okay, so let's just jump right in. And so rings, or most especially commutative rings, can be really thought of as some sort of generalization of the integers. And so since we're going to work towards defining what a ring is, and I just said that they're some sort of generalization of integers, or maybe some sort of category that integers live in naturally, let's look at the integers and some well-known operations, plus and times. In other words, addition and multiplication. Then let's look at the properties of these operations. So first of all, we know that addition is associative. In other words, we know that L plus M plus N is equal to L plus M plus N. So we can do any sort of grouping we want with addition and we get the same result. And then we also know that addition is commutative. So in other words, M plus N is equal to N plus M. And then, well, there are two more important things about addition inside of the integers. And that is that there is an identity element. And in fact, inside of the integers, the identity for addition is 0. And so we've got this element 0, which is an integer where we can do 0 plus n is equal to n. For example, 10 plus 0 is 10, or 0 plus 10 is 10, so on and so forth. And then, well, we also have additive inverses for every integer. So for example, 7 plus negative 7 is equal to 0. The additive inverse can be thought of as like the path back to the identity. So generally, we've got this n plus negative n is equal to 0, and that's going to hold for all integers n. Okay, now let's look at the properties of multiplication, and some of these will be pretty similar. So let's observe that we have associativity of multiplication. So L times M times N is the same thing as L times M and then times N. And then we have commutativity of multiplication. So M times N is the same thing as N times M. For example, 3 times 4 is 12, but 4 times 3 is also 12. And then we have an identity for multiplication as well, and that is the number 1. So we've got 1 times n is equal to n. So 1 times 123 is equal to 123. 1 times negative 13 is negative 13. 1 times 0 is 0. 1 is the multiplicative identity. But let's observe that not everything has a multiplicative inverse. So for example, we know that 2 times 1/2 is equal to 1, but 1/2 is clearly not an integer. It's not a whole number. And so that means that this number 2 does not have a multiplicative inverse inside of the integers. So that's one property that we have with addition that we do not have with multiplication. Okay, so now there's also kind of an obvious interaction between addition and multiplication that you learn maybe in 3rd or 4th grade, and that would be the distributive rule. And we could summarize that as L times the sum m plus n is equal to Lm plus Ln. Okay, so now what we want to do is abstract some of these properties that we've seen into what we will call a ring. But before we do that, I'd like to make a couple of observations. And these observations are related to maybe we have some extra properties over here that are not satisfied by some other natural arithmetic structures. And the first of those will be maybe described best like this. So let's say we make the following replacement. So let's replace the integers with what I'll call 2z. And that's just a way of writing all even integers. So this is going to be like ... -6, -4, -2, 0, 2, 4, 6, so on and so forth. And now if we look over here, all of these properties except for one are still satisfied. And we can kind of see that because if you add two even integers, you end up with an even integer. You multiply two even integers and you end up with an even integer. 0 is an even integer. And then all we have to use is the fact that those are integers already, so these things are satisfied. So anyway, we get closure of the operations, and then we also have the properties that are just inherited from the fact that they're integers in the first place. But one of these properties over here is not satisfied, and that is there is no multiplicative identity. And so there's no element so that if we multiply it to anything, nothing changes. So like over here, when we're talking about all integers, this number 1 is the multiplicative identity, because if we multiply 1 to anything, it doesn't change. So it looks like once we define the notion of a ring, we might have to throw away the need for a multiplicative identity. All right. So now let's look at another case here, and that is if we replace the integers with what I'll call M2x2R, which is going to be the set of all 2x2 matrices where the entries come from the real numbers. So you're probably very familiar with this set of objects from perhaps a linear algebra class. So now I'd like to observe that every condition over here holds that we had before except for one. We do have a multiplicative identity that would be the identity matrix. So I'll just write this 0 or 1 0 0 1 is equal to the multiplicative identity. So before, in our first kind of odd example, there was no multiplicative identity, but we do have a multiplicative identity. But we may not have commutativity of multiplication. And we can see that by the following example. So let's take the matrix 1, 2, 0, 1, and let's multiply it into the matrix 1, -1, 2, 3. And so the standard rule for multiplication of matrices, we'll take this first row, swivel it into the first column. Let's see, this first entry up here will be 5, and then we'll have 5 for the second entry, and then 2 and 3 for the bottom two entries. Now, let's maybe do the multiplication in the opposite order. And so we'll have 1, -1, 2, 3 on the left, and then our 1, 2, 0, 1 on the right. And I'll just maybe get ahead of myself and say that's not going to be equal to what we have above. But what is that going to give us? So that's going to give us the matrix 1, 1, 2, 4. And I'll let you check the details of the calculation if you need to. And if you don't remember how to multiply matrices, well, now is a good time to review that. So let's observe that we have, for instance, if we were to name these things, A and B, and then here we have B and A. So what we have found is matrices A and B, where A times B is not equal to B times A. So in other words, we do not have commutativity of multiplication. And well, I'd like to think that these three structures that we've looked at are fairly natural. All integers, even integers, and, well, these 2 by 2 matrices. And so what we want to do is look at the properties that are satisfied by all three of them, and we'll abstract that into this thing that we'll call a ring. Okay, so with all of that in mind, let's maybe get that definition of a ring written on the board. So after we keep all of those conditions satisfied by those three examples that we looked at, we're left with the following definition, which, like I said, I think naturally rises up from that structure that we saw. So a ring R is a set, I guess I should say a non-empty set. I'll just say that out loud here. So a non-empty set together with two operations plus and times satisfying these conditions for all A, B, C, and R. So first of all, this thing called plus, which is generally addition, is associative and commutative. So A plus B plus C is equal to A plus B plus C. And then A plus B is equal to B plus A. And then next up, there is an additive identity. So in other words, there's this element which we'll call 0. 0 will be the name for the additive identity, so that A plus 0 is equal to A. There's also additive inverses for every element in the ring. So in other words, there is an element minus A in R such that A plus minus A is equal to 0. Then we also have the properties that, let's see, multiplication is associative. So A times B plus C is equal to AB times C. So let's observe we are not requiring a multiplicative identity based off of our first kind of odd example. We're also not requiring multiplication to be commutative based off of our matrix example. Then we've got two distributive rules. We need two distributive rules because multiplication may not be commutative. So we've got a left hand and a right hand distributive rule. So A times B plus C is equal to AB plus AC, and then A plus B times C is equal to AC plus BC. Okay, so next up what I want to do is give a lot of accessory definitions to this notion of a ring. And that will be special types of elements inside of rings as well as some special types of rings. And then of course, as we move forward in the forthcoming videos, we will do some careful study of maybe rings in general, and then these special types of rings as well. Okay, so let's get to these other definitions. Now for our lots of what I'll call accessory definitions. So the first one is if there is an element which we'll call 1 inside of the ring, such that 1 times A is equal to A for all elements A in the ring, we say, well, first of all, that 1 is a multiplicative identity. And we also would say that R is a ring with identity, or a ring with unity, or perhaps we would just say R is a ring with 1. That would be another kind of common thing to say. Now I'd like to observe that there are definitely, or maybe not observe, but just warn that there are definitely like some strange scenarios, as you'll see in one of the exercises at the end of the video, where you have something that looks like a multiplicative identity. In fact, it is a multiplicative identity. So in the sense that if you multiply it to anything else, that other thing does not change, but it doesn't, what I'll say, look like the number 1. So let's just keep that in mind. Then we'll say that R is a commutative ring if the multiplication is commutative. So that's our next definition. Then this is sort of a weird definition right here until maybe you think about some matrix examples you've seen. So a non-zero element A is called a zero divisor if there's another non-zero element B where A times B is equal to 0. And well, I guarantee you've seen some matrix examples like this before. Let's look at, for instance, the matrix 0, 1, 0, 0, and observe that if we multiply that to itself, we get the 0 matrix. So that would be an example of a zero divisor, because in fact, if you square it, you get 0, but it itself is not 0. We'll see some more examples of this a bit later. Next up, a commutative ring with 1 that has no zero divisors is called an integral domain. And so this notion of an integral domain is really where we can have the most clear kind of thought that this whole thing is a generalization of the integers. So next up, we've got this definition of a unit. So a non-zero element A is called a unit if it has a multiplicative inverse. So in other words, if there's this element A inverse in R, where A times A inverse is equal to 1. And so let's observe that, for example, the rational numbers, everything except 0 is a unit. So like 3/4 is a rational number and 4/3 is a rational number. You multiply those together and you get 1, the multiplicative identity. Okay, so next up, a ring where every non-zero element is a unit is called a division ring. And so this thing right here does not require us to have commutativity. If we, in addition, have commutativity, we'll have this notion of a field. So a commutative division ring is called a field. Okay, so now that we've got our main definition over here, and then a bunch of accessory definitions, I'd like to make a picture that has all of the types of rings defined right here, and then look at some examples of types of rings in all parts of that picture. So here's a picture of those types of rings that we just talked about. But that being said, I'd like to introduce or maybe review the notion of z mod n, the integers modulo n, just so that we're okay with some of the examples we'll see that are forthcoming. So I generally do that in my Intro to Proofs class, but we should be able to review it pretty quickly. Hopefully it's already familiar. So let's recall that Zn, or Z mod n, depending on how you want to say it, is going to be the set of all equivalence classes mod n. And so we could write that as bracket 0, bracket 1, all the way up to bracket n minus 1. You can think about that as all possible remainders after dividing by n also if you want to. Then let's just recall that bracket k is going to be the set of all m, where m is congruent to k mod n. And so that means that m and k have the same remainder when divided by n. And generally, when we've fixed a setting of n, so say we're working mod 5 or mod 6 or mod 23, we'll just write 0, 1, 2, 3 up to n minus 1 without the brackets, and just keep in mind that we're working with equivalence classes here, but the simplification is pretty easy. And we'll see that in the review that I'll do with these addition tables for Z5, and then we'll do a multiplication table for Z5 and Z6. So let's start with the addition table for Z5. So obviously if we add 0 to anything, we're not going to change it. That's the additive identity. So here we have 0, 1, 2, 3, 4, and then going down the column 1, 2, 3, 4. Addition is commutative. Well, multiplication is commutative as well. So really we just have to do the top triangle. Then let's see, 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, and then 1 plus 4 is 5. But 5 is congruent to 0 mod 5. It's a multiple of 5, so we would put 0 here. So in fact, 1 plus 4 is 0. So 4 is the additive inverse of 1. Then now we could go down to 2. So 2 plus 1 is 3. 2 plus 2 is 4. 2 plus 3 is 5, which is 0 again, because 5 is congruent to 0 mod 5, and we're doing this reduction mod 5 after every step here. So that's how the addition is defined. Perhaps I should have said that over there. Then 2 plus 4 is 6, but 6 is congruent to 1 mod 5, so that means that we would call this just 1. And then actually, while we're at it, let's just fill in the gap that we are defining L plus K, addition on these equivalence classes, to be the equivalence class of L plus K. And then we're defining the multiplication on the equivalence classes to be the equivalence class of L times K. And you can check that those are well defined. That's generally an exercise in like an intro to proofs class. Then let's do the 3. So 3 plus 1 is 4. 3 plus 2 is 0 again because it's 5. 3 plus 3 is 1 because it's 6. That's 1 more than 5. 3 plus 4 is 2 because it's 7, which is 2 more than 5. And now we can really just keep going, although it's not super interesting at this point. The only new entry is this 4 plus 4, I should say, and that's because we get 8, and 8 is 3 more than 5, so that's going to be 3. Now let's do a multiplication table. So if we do 0 times anything, we're going to clearly get 0, so I can just fill all of those in. 1 is the multiplicative identity, so I can just fill those in very, very easily. And then let's do the rest of them, which are perhaps a little bit more interesting. So 2 times 2 is 4, so that's not larger than 5, so we don't have to reduce it. 2 times 3 is 6, but 6 again is congruent to 1 mod 5, so we put a 1 here. So let's observe that that means that 2 and 3 are multiplicative inverses mod 5. So that means that 2 and 3 are both units. Again, we'll go into this a little bit more carefully when we discuss all of these types of examples over here. Now, 2 times 4, that's going to be 8, but 8 is 3 mod 5, so we'd have a 3 right there. And then I guess we can just fill in that column just like the row because we have multiplication as commutative. Now, 3 times 3 is 9, but 9 is 4 mod 5, so we'd put a 4 here. 3 times 4 is 12, but that's going to be 2 because it's 2 more than 10. We can fill in the 2 here because of the commutativity of multiplication. And then we have 4 times 4 is 16, but notice that 16 is 1 mod 5. So there 4 is its own inverse mod 5. Okay, so now let's go down to Z6. We'll just do a multiplication table here. I'll let you do the addition table if you want to. I've also left off the 0. So here we're going to have 1, 2, 3, 4, 5, and 2, 3, 4, 5 because 1 is the multiplicative identity. Now let's do 2. So 2 times 2 is 4. 2 times 3 is 6, but let's observe that 6 is 0 mod 6, right? But that means that 2 and 3 are 0 divisors. Again, we'll write that down carefully later. 2 times 4. So let's observe that 2 times 4 is 8, but 8 is 2 more than 6. Remember, we're working mod 6 now, so that means that 2 times 4 is simply equal to 2. Now 2 times 5 is 10, but let's observe that 10 is equal to 4. It is 4 more than 6. And now I guess we can fill in this column based off the fact that multiplication is commutative again. Now let's do 3. So 3 times 3 is 9, but let's observe that 9 is 3 more than 6, so that makes that equal to 3. Then 3 times 4 is 12. 12 is a multiple of 6, so that's 0. And then 3 times 5 is 15, but that's 3 more than 12, so we're going to get a 3 there. And then here we can fill in 0 and 3. So just to be really clear here, the operation, maybe what I'd call the naive operation, if you don't want to think about it as doing the equivalence classes, what you're doing here is multiplying these two numbers, then dividing by 6 and keeping the remainder. So in general, it would be adding or multiplying the two numbers depending on addition or multiplication, dividing by n, and then keeping the remainder. It's just the careful way to do that is via these equivalence classes and then those operations on equivalence classes over there. Okay, so let's finish this out. So 4 times 4 is 16. 16 is 4 because it's 4 more than 12. 4 times 5 is 20. That's 2 because it is 2 more than 18, which is a multiple of 6. And then let's see, we'll get a 2 here. And then 5 times 5 is 25. That's 1 more than 24, so that is 1. Notice that 5 is its own inverse here, if you will. In fact, interestingly enough, 1 and 5 are the only things that have inverses. They're the only units in Z6. Okay, so now that we've recalled this Zn, which is going to be super helpful for us, what I'd like to do is go through this picture over here and describe examples of rings that are one type, but not the further down type. So we want to look for a ring that's not commutative and does not have an identity. Or we want to look for a commutative ring that doesn't have an identity. Or a ring with an identity that's not commutative and is not a division ring, so on and so forth. So we'll find things that live exactly in one of these spots, but not further down. Okay, so let's start doing that. So to start understanding this picture, let's start with things with maybe the most structure, these fields. Let's recall a field was a commutative ring with one where every non-zero element had an inverse. So in fact, you're probably most familiar with fields. Let's observe that the real numbers make a field. I think that doesn't really even have to be proven. That's something that we've used, over and over and over throughout studying lower levels of math. Then furthermore, the rational numbers, remember that those are simply ratios of integers, that is also a field. And again, I don't think we really need to do anything there as well. That's kind of obviously a field. But then the complex numbers is also a field. And this is the first place where it might be like a little bit less familiar. So here we have everything of the form a plus bi, where a and b are real numbers, and I is, well, the square root of -1. So in other words, I squared is -1. And so we can check that this is a field. I think it's pretty clear that all of the addition and multiplication characteristics or properties hold, except perhaps the fact that everything has a multiplicative inverse. So I guess you can check carefully that multiplication and addition are commutative and so on and so forth. But that's just really going to be inherited from the fact that it's commutative and so on and so forth inside of the real numbers. So what I'd like to do is just give a brief outline of why everything has an inverse. So let's take something that I'll call z, which is a plus bi. And let's say that's not 0, and that's going to be a complex number. But that means that a is not 0 and b is not 0. So for a complex number to be 0, its real part and its imaginary part also have to be 0. So if it's non-zero, those are both not 0 at the same time. Okay. So anyway, maybe I should say simultaneously. They're not simultaneously 0. Okay, so now let's find the inverse here. So we could just look at the inverse as 1 over z. That would be the multiplicative inverse. But let's observe that that is 1 over a plus bi. But that is not in the form of this complex number here, so it might seem kind of problematic. But in fact, it's not, because we can multiply by what's called the complex conjugate in the numerator and the denominator, and that'll have the effect of putting it in this correct form. So let's observe that if we multiply out that denominator, we'll get something quite nice. We'll get a squared plus b squared. That's because we have a times a, which is a squared. We have bi times negative bi, but the I times I is -1, so that's going to flip a minus sign over into a plus. And then, of course, the cross terms are going to kind of obviously cancel from maybe simple algebra. But now let's observe that this is in the correct form. We could really write it as a over a squared plus b squared minus b over a squared plus b squared times I. And that would be our expression for z inverse, given that z is equal to a plus bi. It's probably a little bit useful to introduce this notion of a complex conjugate, and that would be z bar. That's the complex conjugate, and that's just simply a minus bi. You negate the imaginary part. And in fact, this z inverse can be easily expressed as z bar over something called the modulus of z squared. The modulus of z is this a squared plus b squared. We won't go into any or too many details about the complex numbers in terms of what they do other than these just arithmetic properties, but it's useful to see it like that. Okay, so these are some fields that are probably familiar. R, Q, slightly less familiar, but probably not too bad, the complex numbers. Now there's going to be one more, and that is Z mod P. And that's going to be where P is prime. So that, in fact, is a field. And it's a field with only finitely many elements. So it's our first example of what we would call a finite field. So how could we prove that this is a field? Well, I think it pretty clearly is a commutative ring with 1. And that's because, well, this number 1 serves as the multiplicative identity. And then we just have to check that everything has an inverse. And I think we can check that everything has an inverse pretty easily. Let's take an m, something that I'll call m inside of ZP. But let's observe that that implies that the GCD of m and p is equal to 1. And I guess I should say that this m is non-zero. We want non-zero things to have inverses. Okay, but then let's observe that that means that there exists these two integers that I'll call x and y, where mx plus py is equal to 1. And that's just an equation within the integers. That's so-called Bézou's lemma, that you're able to take a linear combination of two integers and gain the GCD. The GCD here was 1. That's because p is prime. Everything between 1 and p minus 1 is relatively prime to the prime. I'm not checking here that there are no zero divisors. Maybe I'll leave that as a bit of a homework exercise. So next up, what I'd like to do is reduce this thing modulo p. But if we reduce this thing modulo p, let's notice that p times y is congruent to 0 mod p. So reducing mod p is the same thing as putting this inside of zp, and we'll see that m times x is equal to 1. And so that's our equation inside of zp. So, well, that means that we have found the multiplicative inverse for this number m that we started with. Now, how do we find it, calculation kind of way? Well, you have to perhaps use the Euclidean algorithm to solve this equation, and that'll give you this number x, with which you can reduce it mod p and view it inside of zp, and there you have it. Okay, so what have we done so far? Well, we've looked at a bunch of examples of fields. Now let's go up this left branch right here to look at examples of these other structures. Okay, so now we're going up this left branch. So the first thing will be integral domains that are not fields. So let's put that in here. That are not fields. So here we're doing the this but not that as we go up, like I said, this commutative branch of our picture. And in this case, the examples come pretty quickly. So we've got the integers. Okay, well, that's a nice example. We're calling it integral domains, so hopefully the integers are examples of integer domains. We'll notice that ZP is not an example here because that is a field, which we already looked at. So what are some other examples? Well, here are some cool examples like R adjoin X. So this is just polynomials in X where the coefficients come from the real numbers. And so that turns out to be an integral domain. We're not going to check that carefully right now, but that is an integral domain. In fact, if you have F adjoin X, where F is any field, you get an integral domain that is not a field. So that in fact gives us a nice collection of integral domains that are not fields, like Q adjoin X, polynomials where the coefficients are rational numbers, C adjoin X, polynomials where the coefficients are complex numbers, Z 13 adjoin x. That would be polynomials where the coefficients are, integers mod 13, or so on and so forth. Okay, so now let's look at examples of commutative rings with 1. In other words, commutative rings with identity, but with zero divisors. That means that they are not integral domains. So that would live like right here in our diagram. And I think the canonical example here would be Zn, where n is a composite number. And so let's maybe look at some examples of that. Well, notice, let's look inside of Z12. So I'll just put here, in Z12, we would have 3 times 8 is equal to 24, but let's observe that 24 is 0 because it's a multiple of 12. So I could just write 3 times 8 is 0 here. So that means that 3 and 8 are 0 divisors. Let's observe that 1 is just playing the role of our multiplicative identity here, and there's a 1 in each of these. Let's also observe that maybe 6 squared is equal to 0. 6 times 6 is 0, but 6 is not equal to 0. So this is a commutative ring with 1 and also 0 divisors. Now let's go down here to a commutative ring with no 1, but does have 0 divisors. And I think you kind of have to get goofy here, but perhaps the following set. So I'll just call this R for our ring. And let's have it be 0, 2, 4, 6, 8, and 10, seen as a subset of Z12. So let's observe that this is closed under addition as well as multiplication. Maybe I won't really check that. I'll let you check that if you want to, but that's going to make it what we'll call a subring. But let's not carefully define subring right now. We're just trying to get our heads around these definitions. But I'd like to observe that there is no element 1 here. And I guess you have to check that carefully for yourself, but it shouldn't be too bad, just some calculation. Maybe the interesting thing here is everything is a 0 divisor. So let's notice that 2 times 6 is 12, which is 0. 4 times 6 is 24, which is 0. 6 times 8 is 48, which is 0. And 6 times 10 is 60, which is 0, because those are all multiples of 12. So you can also prove kind of more generally, and maybe this will be something that we do when we do some basic proofs involving rings, that if you're a 0 divisor, you cannot be a unit, but the multiplicative identity is automatically invertible. So I guess that gives us a nice explanation why this is a commutative ring, but without the number 1, without a multiplicative identity, but yes for 0 divisors. Okay, so anyway, I think that finishes us going up this left branch. Now let's go up this right branch, which would be maybe what we would call our non-commutative branch. Then furthermore, I would like to observe that there are some things that could maybe connect these branches. Notice that an integral domain as well as a commutative ring with 1 is an example of a ring with 1. So perhaps we could put that connection there as well, but that's kind of neither here nor there. So now we're at this spot in our diagram. So we want a division ring that is not a field. So that means every non-zero element has to be a unit. So here we're going to look at a famous example called the Quaternions. And the notation for that is this H. They're named after Hamilton. And they are all linear combinations of the following objects. We have A plus BI plus CJ plus DK, where A, B, C, and D are real numbers. And for now, let's just think about this I, J, and K as being symbols satisfying the following multiplicative rules. So we have I squared equals J squared equals K squared equals -1. We have I, J, and K multiply in this cycle structure. So what this picture means is the following. If you follow it in this clockwise orientation, you pick up a plus sign for your multiplication. I times J is K. If you go against the arrows, you pick up a minus sign. K times j is negative I, or I times k is negative j. You know, you can summarize it with these rules over here. Now, it's pretty easy to check that everything is satisfied except perhaps the multiplicative inverses. So I'll just write down what the multiplicative inverse of a non-zero element is, and then I'll in fact let you check that this is the multiplicative inverse. So this is going to be 1 over a squared plus b squared plus c squared plus d squared. So we know that that's non-zero in the denominator because we're starting off with something non-zero. And then we have a minus bi minus cj minus dk. So it's got that feel of the multiplicative inverse for complex numbers for sure. So all you have to check is that if you multiply this right-hand side into this thing a plus bi plus cj plus dk, you get the number 1. Everything cancels nicely. So I think that's probably a nice exercise that I'll leave you with. But now we'll finish this thing off with a non-commutative ring with multiplicative identity, but where there are 0 divisors. So that would live right here. It's not a division ring. And then we need a non-commutative ring with no identity. So that would live up here. It doesn't go down any of the paths. And here we're going to use a similar example for each. So for the first one, let's take m 2 by 2r. So that's simply equal to 2 by 2 matrices with the entries in the real number. So I'll just put dot, dot, dot there. We defined that on the board already. And so there is a 1 that is the identity matrix, and then we know that it's non-commutative. We saw an example of that before. Now, what about a non-commutative ring without a multiplicative identity? Well, we can take some inspiration from some of our previous examples and just maybe like glue them together. So let's say maybe m 2 by 2 with entries in 2z. So that would be something of this form. Maybe 2a, 2b, 2c, 2d, where a, b, c, and d are all integers. So in other words, we've got 2 by 2 matrices, but every entry is an even integer. I think you can pretty easily check here that there will be no multiplicative identity matrix in this case. And also it's non-commutative kind of clearly. All right, so good. I think that we've maybe populated some nice examples for all of these. So now what I want to do is leave you with some exercises. Okay, so here are 4 exercises based on what we did today. The first one is really just a calculation. Actually, number 1 and number 3 are calculations. And so let's find the product of these two polynomials in Z5 adjoin X. And so that means that the coefficients are viewed as being in Z mod 5. So just keep that in mind as you're doing this calculation. Next up, here's like a nice kind of simple general result. Let's show that if n is composite, then Zn is not an integral domain. So we already showed that if it's prime, it is an integral domain because it was a field. Well, in fact, it's not an integral domain. It has 0 divisors if n is composite. So obviously, you're going to have to use the factorization of n for that. Next up, this will prove that inverse relationship in the Quaternions, and that is that a plus bi plus cj plus dk times a minus bi minus cj minus dk is equal to a squared plus b squared plus c squared plus d squared. So do that calculation out, keeping in mind how I, j, and k multiply with each other. So that'll prove that inverse relationship that we wrote on the board, because you can simply divide that right-hand side by, well, itself when it's non-zero. Then here's kind of a mind-bending example for the fourth exercise, and that is if you take this set R, which is 0, 2, 4, 6, 8, 10, 12, as a subset of Z14, that's in fact an integral domain. And so How will you show it's an integral domain? Well, I would first find the multiplicative identity. We usually call that multiplicative identity 1, but notice there's no 1 here. So that means that one of these numbers plays the role of the multiplicative identity. And then after you find that multiplicative identity, you want to show that everything has an inverse. And you can do that explicitly by finding an inverse element for all of those non-zero elements. And that's a good place to stop.